Welcome to the video on solving polynomial equations. Let's get right into it. The first thing that we need to talk about is the fundamental theorem of algebra. Sounds pretty important, but it's actually something that we probably have been talking about for a while. Basically, what it says, a corollary of it, is that an nth degree polynomial equation has n complex roots. So if it's a cubic equation, meaning it's a third degree, it will have 3 complex solutions. Let's get into this then. We have an equation here, and we want to solve this by factoring. Notice that we have 64x cubed minus 27. That's the difference of cubes, and we're looking to solve for x that are elements of the complex numbers. So basically all the solutions to this. Okay, when we have the difference of cubes, I'm going to need to factor that to solve for all the solutions. So this is really 4x that's been cubed, and 27 is really 3 that's been cubed. That means that this factors into 4x minus 3 times 16x squared plus 12x plus 9. And I knew that because I've memorized how to factor the difference of cubes. So now that this is factored, I'm going to set each of these factors equal to 0 in order to solve for all 3 solutions. So my first solution over here, we're going to get 3/4. And over here, this quadratic is never going to be factorable, so I'm going to have to use the quadratic formula in order to find the non-real solutions. So I've plugged into the quadratic formula, and I just need to simplify this. And in here, this is negative 432. That's our discriminant over 32. And I wouldn't worry about simplifying this, but I definitely would want you to write this with that imaginary component, so I'm going to take the I out, if you will. And that's really 2 solutions, so in total we have our 3 solutions. On to the next method. Okay, so for our second method, we're going to actually use our graphing calculator to help us to find some answers. Maybe we can find all 3 answers, or maybe we can't. We're actually going to graph that in our calculator, and you'll see that's right here. I went into y equals, and I put the left side of the equation in already, and I hit graph, and I can see the graph. So I can definitely see A0. If I want to maybe go up a little bit further here, let's go up to 100. See if I can see anything else. Oh, I can actually verify that that's going to be our only 0. So let's come back here. And let's make note of that. We know that x equals negative 4. And I actually got that by looking at the table before making the video, but you would obviously double check that that's where the 0 was. I know that that's one of the solutions, which also means that x plus 4 must be one of the factors. Well, how am I going to find this other factor? That's where synthetic division comes in. So let's come over here and do some synthetic division. So let's see, negative 4, and the coefficients here are 1, 1, negative 7, and 20. So here we go. Bring in that 1, multiply. We get negative 4. Now I'm going to add these to get negative 3. Multiply these to get 12, add these to get 5, multiply these to get negative 20, and perfect, my remainder is 0, which means that x plus 4 was a factor, leaving the other factor to be x squared minus 3x plus 5. Beautiful. Now I can use this other quadratic to find the other two solutions, just like we did before on that other question. I'm going to set that equal to 0 and use quadratic formula. Okay, so I've plugged into my quadratic formula. I'm just going to simplify everything now. What is that? 9 minus 20, so negative 11 over 2. I'll just write that as 3 plus or minus I root 11 over 2. And that's two solutions. Up here was 3. That's all she wrote on that one. On to our next example. Okay, so we have another graphing example. This one looks a little bit more complicated. It's not equal to 0, and it also says solve for x, where x is an element of the positive real numbers. So we don't really care about those non-real solutions on this one. So a graph is actually going to be the perfect way to solve for this. The graph gives us those real solutions. I'm just going to graph this. We're going to put the left side into y1, the right side into y2, and see what happens. I actually set this up in Desmos already, so I'm going to pull that up right here. You'll see that this is y1, this is y2, and we're looking for where these two graphs intersect. Now, this is a cubic equation. You'll notice that if we put the left side into standard form, it would get you a cubic, same with the right side. So we should be seeing 3 intersections if there were 3 real solutions. Remember, they don't all have to be real. There's have to be 3 complex solutions. If I actually move this around, you'll see there's an intersection here, here, and here. Perfect. So we see all 3 intersections, but don't forget, we want the positive real solutions. So I only see 1 where they are intersecting and the x value is positive. So the answer to this would be 1.705. Even though there were other real solutions, they weren't positive. So make sure you're paying attention to what types of solutions you're looking for. Okay, we have one more theorem that we need to cover. It's called the rational root theorem. I may have alluded to this in class already. Basically, this is saying, here's a polynomial equation in standard form, right? The degrees are going in decreasing order. If there's going to be a rational root, right, meaning that you can write it as a fraction where those numbers are integers in the numerator and denominator, it has to be of the form p over q, where the p is a factor of this coefficient right here. In other words, the constant, and q is a factor of the leading coefficient. So here we have an example. If this has rational roots, if it does, so I'm going to write down possible rational roots. We can actually make a list of those things. So on the top of the fraction, we're going to put the factors of this number. And in the bottom of the fraction, we're going to put the factors of this number. So let's start it off easy. We know the factors of 8 are plus and minus 1, plus and minus 2, plus and minus 4, and plus or minus 8. Right? Those are all the possible numbers that could go in the numerator. And then the denominator would be the factors of 7. Well, that's a pretty short list, right? We get plus and minus 1, plus and minus 7. So let's split those up now. Let's do all those different combinations. So if the top was a positive 1 over positive 1, we'd get 1. If it was negative 1 over positive 1, we'd get negative 1. So we'd get plus or minus 1 as a possibility. I'm going to go a little faster now. We could get 2 over 1 or negative 2 over 1, so plus or minus 2. We could get plus or minus 4 from this combination right here, or plus or minus 8 from this combination right here. But that was just if we used plus or minus 1 in the denominator. We might also have a 7 or a negative 7 in that denominator. So let's go through this again. We could have plus or minus 1/7, plus or minus 2/7, plus or minus 4/7, or plus or minus 8/7. That's a list of actually 16 possible rational roots. So if it didn't have a rational root, it could have an irrational root, that would still be real, or it still could have non-real roots. Let's move on and actually start to test some of these things out. So there's that same equation, and we want to solve for all of the complex solutions, okay? In other words, roots. Those are really synonymous. We made a list of things. Let's test them out using synthetic division. I always like to start low, and I usually start positive too. So let's test out, is 1 a rational root of this equation? Just doing synthetic division here. I just have this feeling that this is not going to work out. Oh, and I was right. Yep, that is not 0, right? Isn't that negative 21? No good. Let's try 2. Setting up my synthetic division now to see if 2 is a possible root. Oh, this is definitely worse. I'm stopping right now. How about 4? Try that. Oh, I have a good feeling, right? It's like these big numbers just turned into a small number. And look at that. We have that remainder of 0, which means that 4 is an answer, right? X equals 4 turns out to be a root. I'm not going to sit here and test the other ones out. If I have a root, that means I have a factor, right? So I know that this thing factored into x minus 4. And what would this get me here? This would get me 7x squared minus 2x plus 2, right? That's really what the equation is. So we have this quadratic here. I'm just going to plug this stuff into quadratic formula and see what we get. Right there, our b value is negative 2. So there's 2 plus or minus negative 2 squared inside the square root, minus 4 times 7 times 2, all over 2 times 7. We'll simplify that. 4 minus 56, and 4 minus 56 is negative 52. So there we can see that there weren't other rational roots, they were just possible rational roots. So it would have been wasting our time to test the others out using synthetic division. Obviously, if this hadn't been a quadratic, let's say it had been a cubic or a quartic, I would have to keep trying some roots. I used the quadratic formula here because that's the easiest way to solve a quadratic that's not factorable, right? So this could be a little bit more difficult, but I think we've seen the basics, and you're going to definitely do more in class. We will see you then.